Use trigonometric functions in applications. Well, so let's have a look at a couple of word problems. What do we have? The palm trees are easy to transplant relatively to similarly sized broad-leaved trees. At one tree farm, palm trees are harvested once they have reached a height of 20 feet. And otherwise, if their heights are lower than that value, well, they can't be harvested yet. Suppose a farm worker determines that the distance along the ground from his position to the base of the palm tree is 22 feet, which is this distance right here, that horizontal distance. Also, let's see. He then uses an instrument called a clinometer held at an eye level that is 6 feet to measure the angle of elevation to the top of the tree, and he finds out that the angle is 30 degrees, 30.2 degrees. Now the question here is the tree tall enough to be harvested? Well, let's find out. So here we're going to use right triangle trigonometry to solve this problem. Well, and we kind of have an imposed right triangle here. However, check this out. Notice that a clinometer, it's not at ground level, it's actually 6 feet above the ground, that is on his eyes. That means, well, we're going to look at this triangle right here, which is this one right there. Okay, let me do this. And well, we are already given some pieces of information, 30.2 and 22 for the distance between the person and the tree and the palm. And we have the height of the triangle, but need to be careful because that whole h right here is the height of the palm. But in this case, the height of the triangle, let's just call it y for now. All right? Call it y. And well, so that's going to be our unknown value here. That is, well, we need to know the value of y. So in this case, we are going to look for a trigonometric function that relates, in this case, the opposite side and the adjacent side, given in this case an angle right here, which is 30.2. Oh, I need the degree symbol, otherwise it would look like a radian. Any ideas on what trigonometric function relates opposite and adjacent? Tangent, right? So in this case, the tangent function, the tangent theta, the tangent function equals opposite over adjacent. All right? Now, from here, okay, how about we write down tangent theta using our labels from the triangle, that is y over 22. And well, all we do to find the height of the triangle, not the height of the palm tree, be careful, that's going to be y equals to 22 tangent of 30.2 degrees, all right? Be careful because notice we have degrees in our pieces of information. So when it comes to using the calculator, and in fact we have to use the calculator for this because we have an angle that it's not an exact angle. However, if it were a 30-degree angle, well, we know how to get those results from the unit circle or the reference triangles. Well, so let's go to the calculator. Make sure to be in degree mode. Well, in fact, my calculator is already in degree mode. So, second quit. So that's going to be 22 tangent of 30.2. Close parentheses. Click enter. Final answer, that's 12.8. I'm going to round to one decimal place. So this is approximately 12.8. But again, that's only the height between the eyes of the person looking at the tree, at the palm tree, and the highest point on the palm. We still need to add 6 feet here, so this is 12.8 plus 6, so the height of the tree, that's equal to 12.8 plus 6, which is 18.8 feet. But now that's not just a question. The question is the tree tall enough to harvest? Well, again, they can be harvested if they are at least 20 feet, so this tree is not ready yet. Not ready to harvest. Okay? Let's look at another word problem, the one on the last page of the handout. Well, example number 6. A pilot flying an airplane at an altitude of 1 mile sights a point at the end of the runway. The angle of depression, that is, when the descending angle at which the airplane is about to land, is 3. Well, actually, it's 3 degrees. I forgot the degree symbol, but at least the degree symbol is there on the picture. What is the distance d from the plane to the point on the runway? All right, so that's the question. Round to the nearest tenth of a mile. Well, so in this case, you need to be careful about how we treat this problem, because check this out. We have this triangle right here, which for this angle we know this is 90 degrees. All right, that's a right triangle. All right. That's a right triangle, and well, we know that this angle between the airplane and the glide slope, in this case that is the slope at which the airplane is gliding to land, well, that's 3 degrees. However, we know by complementary angles that this is the addition of these two angles is 90 degrees. So if this angle is 3 degrees, the complement of 3 degrees will be, in this case, 87 degrees, all right? Well, in this case, what are they asking us to find? Well, so they're asking us to find this distance right here, and check this out. If this is our reference angle, how can we find this distance here? So which trigonometry, well, because what else are we given besides the angle, which is 87 degrees? We are given one of the sides, which is the adjacent side to the angle. We're being asked to find the hypotenuse. Which trigonometric function relates the hypotenuse and the adjacent side? What is that? Cosine. So cosine theta equals adjacent, which is 1 over hypotenuse, which is d. And well, in this case, we may need to, well, let me write it in words. Adjacent over hypotenuse. And then, so cosine, what's that? 87 degrees equals the adjacent, which is 1 mile, times the hypotenuse, which is the distance d. Now careful, because we need to solve for d in this case. Multiply both sides by d. And from there, that's d cosine 87 degrees equals to 1. And then to get d by itself, how about we divide both sides by cosine 87 degrees? Not just 87, because if we say just cosine 87, we would be saying 87 radians. That's a whole different story, right? Just careful with that. Cancel or divide out these cosines on the left-hand side. That's going to leave us with d equals to 1 over cosine 87. And how about, 87 degrees. How about we just type that on the graphing calculator? I know what you might be thinking. Yes, you have a trigonometric function in the denominator. If you move it to the numerator, what's that going to be? Is that going to be a secant, because that's the reciprocal? But recall that we don't have a secant key on our graphing calculator. What do we have to do? Well, go back to 1 over cosine. So let's just punch it in on the calculator. So that's 1 over cosine of 87 degrees, and that has to be about 19.1. 19.1 miles. pretty basic problems, just selecting the correct trigonometric functions that relate the information that we're given and the information that we're being asked for. All right, so with this we finished section 4.3. Let's move on to section 4.4. All right, 4.4. Okay, trigonometric functions of any angle. So what do we do in this section? Evaluate trigonometric functions of any angle. That's number one. Determine reference angles. That's maybe the new thing we're going to learn. Because you will find out anyway that what we're doing in sections 4.3 and most of what we're going to do in 4.4 is repetition of 4.1 and 2 and 3. And again, that's to pretty much put together all the information. How do we use it, whether from the triangles or whether from the circle, which can be a unit circle or a circle of radius r, whatever the radius is. All right. So, and I believe this was our first point of view for defining angles on a circle of radius r, because check this out. This point right here is essentially a point on a circle of radius r. All right, so that's our radius r. That doesn't look like a circle. Let me make it look like a circle. Much better, I guess. All right, and well, so but now we're going to, instead of looking at the circle per se, we're going to just look at the ray formed, or rather the angles formed by the two rays. The first ray, which is the positive x-axis, and then the second ray, which is any other ray forming an angle in whatever quadrant it is. All right, so let's see. And so in this case, what we're doing is centering a circle, or rather imposing a circle in standard form. What's a circle in standard form, by the way? Well, a circle in standard form is a circle of radius r. Could be a unit circle, could be a circle of any other radii. And well, what makes it standard is that the center is at the origin. So pretty much every point, what we will do is find the distance between 2 points, the origin and whatever point is there. And well, in fact, that's no other than the result of using Pythagorean theorem, as we can see in this expression here. It looks a lot like very Pythagorean-ish, right? And so let's see. And again, we're going to define, since in this case, check this out. This projects a triangle here for which this is x and this is y. Of course, it's technically negative x because it's going on the left-hand side, but well, we can fix that later when we have more concrete values. And again, sine, which is the opposite over hypotenuse, that's the opposite side of the angle, y over hypotenuse, which is r. Well, it's already labeled there. Cosine, adjacent over hypotenuse, that's adjacent over hypotenuse. Tangent, opposite over adjacent, opposite over adjacent. And well, the reciprocals come, or the other remaining three functions come from taking the reciprocals of those values, as we've seen in the previous sections, of course. All right, how about we do an example? Let the point P, -2, -5 be a point on the terminal side of the angle theta drawn in standard position. Find the 6 trigonometric functions. Well, how are we going to go about this one? All right, so let's first of all impose a trigonometric, no, not a trigonometric, a Cartesian plane. And let's locate this point, -2, -5. All right, so that's going to be -2, 1, 2, 3, 4, 5. So essentially, we're going to obtain the following ray. So this ray right here. All right. And in this case, let's let's go about it. Essentially, we are creating this angle here, right? Between the angle between the positive x-axis, that's also angle in standard form. That is the angle that is formed with the positive axis, and any other ray for whose common point in common, that is the vertex, is also the origin, the point 0, 0. All right, so that's the point. -2, -5. So we need to know r, and to get r, that's the square root of x squared plus y squared. And well, the square root of x squared, that's -2 quantity squared plus -5 squared. That equals the square root of 4 4 plus 25, which is the square root of 29. And well, in this case, we can't reduce the square root of 29. Number one, the number 29 is a prime number. Unlike other numbers, if it were 28, for example, that's 4 times 7. We can take out the square root of 4, which is 2, but not in this case. All right? So let's see what's next. So that's r. So we have x equals -2, y equals -5, and r equals to the square root of 29. And we have all the information we need to get the 6 trigonometric functions. All right, so by definition, sine theta in this case, that's y over r, and in this case, y in this case is -5 over the square root of 29. But again, as we discussed many times already, Alex may not like radicals in the denominator, so you might want to rationalize the denominator. Whoops. Rationalize the denominator, and that's -5 root of 29 over 29, root of 29 times itself, just bring down the 29. What about cosine? Cosine theta, which is the ratio not y over x in this case, it's x over, no, I mean not y over r, it's x over r, and our x is -2 over the square root of 29. And well, again, you might want to rationalize the denominator by multiplying by the square root of 29 over both in numerator and denominator. That's going to leave us with a similar result as before. That's -2 root of 29 over 29. Tangent, on the other hand, tangent theta is the ratio between y and x. And well, the ratio y to x, that's a -5 over -2. No need to rationalize anything because no radicals involved. However, you might want to reduce the minus over minus, and that becomes a plus, 5/2. So those are the first 3 trigonometric functions, the 3 basic ones. The remaining 3, cotangent, secant, and cosecant, are just reciprocals of the other 3 functions that we just defined. Let's go ahead and find those. Oh shoot, don't have enough space. Let me make some room. All right. Okay, so cotangent theta, that's the reciprocal of tangent, that's x over y, and x, which is -2 over -5, which is y, that's 2/5. Secant, which is the reciprocal of cosine, and let's go back to the cosine function. The cosine function, which is x over r, secant is r over x. And that's r, which is the square root of 29, divided by the quantity x, which is -2. And well, in this case, we're done because no need to rationalize any denominators because the radical factor is in the numerator, not in the denominator. And last but not least, we need to define the cosecant function, cosecant theta, which in this case is the reciprocal of the sine function. Recall sine is y over x, so I mean y over r, then r over y equals cosecant, and r in this case is again the square root of 29, which is great because we don't have to rationalize anything, divided by negative 5. And well, we can just have this negative in front of it. Final answer. Right. This is how we get the 6 trigonometric functions from a given point, and on finding that radius that goes from the origin to that given point as the hypotenuse, if we will. And again, we can always relate it to what we did before. Check this out. We can relate this to a right triangle, for which this is theta. This is -2, -5, and what was that? The square root of 29. Same thing. All right, same thing. Let's see what's next. Okay, determining reference angle. So this topic is finally new, you know, from what we've been doing for the entire chapter. And finding reference angles is really useful when it comes to evaluating trigonometric functions of angles that are outside of the first quadrant, you know, because usually evaluating sine or, well, any trig function for 30, 60, and 45 degrees, well, just go with the values of the unit circle. You guys have memorized those values. However, or use the special triangles. However, what if we are somewhere in another quadrant? Well, so how about we define what a reference angle is first? So number one, so if we have an angle theta in standard position, that is formed by the two rays, again by definition, where it starts at the positive x-axis and then finishes wherever it goes after the rotation given theta. The reference angle is the acute angle theta prime formed by the terminal side of theta and the horizontal axis. Well, we're going to see this in a picture in a second. Well, how about we see this in action looking at a couple of examples. So number one, let's check this out. Cartesian plane. Let's draw a Cartesian plane. And well, 135 degrees, I believe, is in the second quadrant, isn't it? Does that sound about right? All right. Because, well, yes, that's 90 degrees. 100, 120 degrees, yes, 135 degrees, it's right here, all right? Now, here is what we want to do. We want to find the reference angle, that is the angle formed by this ray, by the terminal side of the angle, and the x-axis, the horizontal axis. Check this out. Notice it doesn't say the positive x-axis. It says the x-axis only. And well, so here, because check this out. Here, we have what kind of angle? What kind of angle? This is an obtuse angle, and this is the acute angle. That's the angle that we're finding. That's going to be the reference, the reference angle, the acute angle formed by the terminal ray, the second ray, and the x-axis, whether it's in the positive side or the negative side. It really doesn't matter. All right. So let's find that reference angle. Well, 135 degrees. Notice it's pretty close to 180 degrees. The question is, how far away is 135 from 180? What do we need to add to get? So what do we have? We have a 45-degree angle, or a pi over 4, for example. So knowing this reference angle from here, you can already you can already tell the values of the trig function, but we are not evaluating the trig functions yet. We're going to do that in the next topic. So what we want to do in this case is write down theta prime, which is the reference angle. So we are going to use a 45 degree angle as a reference to do whatever calculation we need in later. All right. We can do the same thing with negative angles, like letter B. Number one, Cartesian plane. Draw a Cartesian plane, and in this case, careful because it's a negative angle. For positive angles, we go in the counterclockwise direction. As opposed for negative angles, we go in the clockwise direction. All right. So 95 degrees. Hold on. All right. So if I turn all the way in this direction, check this out. This is 180 degrees, isn't it? Or rather, negative 180 degrees. So I need, how many more degrees do I need to get to negative 185 degrees? So I need an angle of, 15 degrees, right? So that's the angle. So that's our reference angle. Theta prime equals 15 degrees. Okay. Well, of course, those 15 degrees is not one of those nice angles like 45, 30, and 60 degrees. However, later we are going to evaluate and we are going to obtain exact values. So you can say there are nice values, but we don't know them yet. We're going to get those when we use half angle formulas, double angle formulas, addition of angle formulas. Well, you'll see. All right. Theta equals negative 5 pi over 4. Well, careful because this time we're now using radians, and on top of that, it's also a negative angle. All right. Cartesian plane. And, well, negative 5 pi over 4. So let's check this out. How about we write down negative 5 pi over 4 as negative 4 pi over 4 minus pi over 4. All right, do we agree that negative 5 is negative 4 minus 1? Well, this way we can see that this negative 4 pi over 4 is the same as saying negative pi minus pi over 4. What is that going to mean? Well, check this out. It means that we're going to go negative pi, and then from negative pi we're going to do another pi over 4, but in this case in the negative direction, and that's to get this angle right here, which actually, check this out, happens to be the same reference angle for 135 degrees, except for we're calling a different angle, and we're going in the opposite direction, and well, coincidentally we're getting back to the same point. And again, we already seen this before. This is a 45 degree angle, so in this case that reference angle is theta prime equal to 45 degrees. What is that useful for? You might be asking yourselves. Well, sometimes it's a little hard to come up with sine or cosine or whatever trigonometric function for 135. You're like, oh, hold on, what's this? Yeah, I'm not sure it's this or that. Well, I have a hard time getting these trig function values, don't get me wrong. So I'd rather instead use a reference angle, and that is a value for which we are more familiar with, their trigonometric function values, and then just impose those values to the corresponding quadrant and then change the signs of the corresponding values. I think that's going to be the next topic. Yes, evaluating trigonometric functions using reference angles. Okay, there's a couple of things we need to take into account in order to evaluate this using reference angles. Determine the function value for the reference angle theta. All right, after finding the location where the angle is at, modify the trigonometric values. All right. Well, determine the number 2. Fix the appropriate sign based on the quadrant in which theta lies. Well, and I left some space here for something pretty cool that you may have seen before. The textbook gives you like a lot of signs in this in this quadrant and a lot of information, but I want to make it a lot more summarized. Maybe you've seen this before. That's hold on. That's A S T C. Have you seen this before? And a mnemonic to memorize this is all students take calculus. But what's that? The A stands for all. All functions are positive. All trigonometric functions are positive in the first quadrant because what do we have in the first quadrant? Positive x and positive y. All right, that's why all functions are positive. Now, what about S? S stands for sine and its corresponding reciprocal cosecant. That means only sine and cosecant are positive because what do we have? We have a negative x, and recall that the x component of the points on the unit circle, or the x component of the side of a triangle, relates the cosine function. And well, y is positive, that means sine is positive. On the one hand, tangent is the T stands for tangent, and of course it's reciprocal. Cotangent is positive in the third quadrant. Everything else is negative because check this out. What do we have on the third quadrant? We have negative x and negative y. So both sine and cosine are negative. However, since the ratio since tangent is defined as the ratio between sine and cosine, we are dividing a negative by another negative. What do we get as a result? We get a positive. And likewise, last but not least, the fourth quadrant, which stands for C, that's the cosine function, and of course its reciprocal secant. Those are the only ones that are positive, and that's because we have positive x, negative y, right? Positive x and negative y. So let's see. Since y is negative, sine is since sine is negative, that's because the y component is negative. All right. So just memorize the ASTC to find out what is the sign of the components, or of the sign. Yes, the sign of the points. Well, you'll see. Evaluate the given function, sine of 240 degrees. Well, so for sine up to 40 degrees, let's do a Cartesian plane first. And draw the 240 degree angle. Well, the 240 degree angle is going to go past the 180 degree. In fact, 240 degrees, 240 degrees is 180 plus what? Plus 60 degrees, I believe. Okay, so it's going to go like this. 180 degrees, 60 degrees, so that's going to be our 240 degrees. Well, let's focus on this triangle right here, and I'm going to draw that triangle on the side. Well, you know what? I'm going to leave it here. Well, notice this. This is the reference angle is in this case 60 degrees. Right? That's the reference angle. Now, check this out. Number one. We are working on the third quadrant. What is the sign of the sine function in the third quadrant? Is it positive or is it negative? Remember, ASTC, all students take calculus. So what's the only function, what's the only positive function in the third quadrant? So what about sine? Is that positive or negative? Okay, so this is what we're going to do. Check this out. Sine up to 40 degrees, it's exactly the same thing as sine of 60 degrees in the third quadrant, but it happens that at that quadrant is negative, okay? If you evaluate those two quantities on your graphing calculator, you should get the same thing. Now, what's 60 degrees, or what are the components in this case? Well, so in this case is the point, the given order pair, it's going to be for x is negative 1/2, and negative root of 3 over 2 for the y values. Those are the values that we learned from back in the when we were doing either the triangles or the unit circles. So recall that sine is a y value, so final answer negative root of 3 over 2. And you can verify this result with that page with the unit circle you got from section 4.1. All right, final answer. Let's look at the next example. So for the next example, tangent of negative 225 degrees. All right, 225 degrees, that's for sure negative, a value that is larger than 180 degrees. That is, we're going to go from zero, and actually since it's a negative angle, we're going to go in the clockwise direction. Now 180 plus what? 180 plus what value equals 225? Is that 45 degrees, I believe? Okay, so I'm going to go negative 180 plus 45 to reach negative 225 degrees. So it's going to be this angle right here, which in this case, it's going to have, well, a corresponding order pair actually. Number one, what's the sign of the tangent function in the second quadrant? It's negative because only sine is positive, right? Well, so in this case, well, let's see. Actually, the point is root of 2 over 2 comma root of 2 over 2. That's always for a 45-degree angle or a multiple located on another quadrant. However, need to be very careful because the second quadrant contains a negative x and a positive y. All right? So, well, they're asking us to find the tangent function, and we know that tangent is sine over cosine or y over x. Either way, using identities, sine over cosine, or using the ratios from the definitions in terms of r, x, and y, you should get the same thing. However, first of all, we need to define to redefine tangent of negative 225 as tangent of 45 degrees, but since in this case we are working on the second quadrant, we know this is going to be negative. All right? Well, so tangent of 45 degrees, it's actually 1, but this is negative, that's just negative 1. All right? Oh, the next one, letter C. Secant of 11 pi over 6. So for 11 pi over 6, oh, there's 4 of them. I thought there were only 3. All right. Cartesian plane again. What's that? Okay. So 11 pi over 6 it's almost 2 pi because 2 pi in terms of pi's over 6, that'll be 12 pi over 6, right? So that should be in quadrant number 4. So I'm going to go like this. From 0 all the way to almost 2 pi. All right? And well, that's our number 1. That's at 11 pi over 6. Oops. And that's our, what's that, 30-degree angle. All right? Okay, so let's have a look at this. In this case, for a 30-degree angle in the fourth quadrant, well, actually, we are not going to evaluate the secant function. How about we evaluate the 1 over the cosine function instead? All right, that's a 1 over well, you know what? Let's do the secant function first. Secant, well, secant of 11 pi over 6 is exactly the same as evaluating secant of 30 degrees or pi over 6. Now, do we need to turn this into a negative? Is the secant function negative on the fourth quadrant? So we don't need to fix the sign the same way we did for examples letter A and B, because it turns out that the signs are the same. Secant of pi over 6, that's 1 over cosine of pi over 6. And cosine of pi over 6, from the unit circle, we know that this is root of 3 over 2. And well, that's one of those weird numbers, so dividing by a fraction, make sure to multiply by the reciprocal. That's 2 over the square root of 3. And well, rationalizing the denominator, we get the following. We get 2 root of 3 over 3. All right? There's one more example. Oh, there's 5. Huh, interesting. And then what's in there? A couple more. Yeah, we can do those. Okay, let's do one more of this. Secant of 9 pi over 2. All right, need to be very careful with this one, because actually this is going to be a really, really big angle that is actually going to go past 1 rotation, maybe even 2 rotations. I don't know, but it's big. We'll find out. All right, that's let's see. So 9 pi over 2. How about we rewrite it as secant, secant of 8 pi over 2 plus pi over 2. Do we agree with this? But hold on, check this out. 8 pi over 2 reduces to 4 pi plus pi over 2. What is the 4 pi going to tell us anyway? Any ideas? 2 rotations, right? So that means, oh, hold on. 2 rotations. 2 complete rotations, and then an additional pi over 2. So we will end up being at pi over 2, somewhere here, but after 2 rotations. So let's represent the 2 rotations first in green for the original angle. That's 1 rotation, 2 rotations, and then go to pi over 2. So that's our, first of all, 9 pi over 2. Now our reference angle in this case is going to be pi over 2, whose point on the unit circle is 0, 1. All right? Well, in this case, well, no, no need to change any signs because it's a quadrantal angle. It's not an angle on a sine. Well, yes, technically the positive y. Never mind. Well, so this is the same as saying secant of pi over 2. Now, to evaluate the secant of pi over 2, well, from the top of my head, I can't evaluate secant of pi over 2. How about we use identities in this case? We know secant pi over 2 is the same as 1 over cosine of pi over 2. All right, from the unit circle, what's cosine of pi over 2? 1 over 0. So that's going to be 1 over 0. And what's 1 over 0? Undefined. All right. Let's do letter E.